Hi guys, this video will be a full cover-up of translation software as per Unit 16 of the Cambridge International Examinations 9618 A2 level computer science syllabus. To jump in, let's give ourselves a quick recap of what translation means and the overall process and components involved in translation. Take a look at the diagram that you see in screen. This diagram is an effective summary of translation as per the syllabus. Let's begin. Now, in this process, you start off with source code. Right? You start off with source code. Now, what exactly happens with this source code, guys? The source code in translation has to eventually get converted into binary. That's the purpose of translation in the first place, to convert source code into machine code or a form of code that can be understood by the computer, which in turn is binary. Now, in order to convert source code into this binary, you can either convert it using an interpreter or a compiler. If you use an interpreter, the source code is converted line by line and executed then and there, which means that the source code is loaded to RAM and executed line by line. So the translation process takes place actively during execution. But source code that takes the compiled route would convert into an executable or an intermediate form, which can then be executed later on. So as a result, source code that uses a compiler would produce an executable file or some form of intermediate code that can be run later, whereas an interpreted form of source code needs to execute then and there. An example of programming language that supports interpretation is Python, and an example of programming language that supports compilation is Java or C++, right? Now, of course, the process of compilation is pretty straightforward, but we'll remind ourselves of compilation later on in the slides as well. But what we need to understand next is compilation is also not a very straightforward route, because compilation can take one of two routes. Compiled code can either be converted to object code and then linked to library programs and then be converted to an executable, or compilers may produce intermediate code, which can then be run via a virtual machine to interpret the final intermediate code to run it in the RAM directly. So the compiled languages that you have heard of may either take the object code route or the intermediate route. But again, the choice of which we choose, the choice of which we do, depends on the language itself. So for example, C++ tends to follow this object code route, but Java tends to follow this intermediate code route. But again, guys, this is a quick summary of translation where you start off at source code and you produce either an executable file or you run the code directly. If you take the interpreted route on the top of the diagram, you'll be running the code line by line while you're interpreting it or while you're translating the program. Or if you take the downwards bottom route, you'll be compiling the code either into object code, which next needs to be linked with your library programs to produce the machine code, or you can take the intermediate code route like Java, for example, does to produce some sort of intermediate code, which is in Java's case known as bytecode, and then converted into executable or run then and there via a virtual machine that uses an interpreter. Or it may also use something called a JIT compiler, which stands for a just-in-time compiler. But again, you don't need to know these terms. These are just examples of different softwares used for the intermediate code execution. But that's the overall idea of translation. Now, having understood the overall process, let's remind ourselves of what object code, intermediate code, and machine code means. Object code is platform-specific, machine-readable binary, right? It's platform-specific, machine-readable binary generated by the compiler, as we saw in the previous diagram. But it's called object code because it's somewhere in the vicinity of assembly, where it's not completely binary yet, meaning the code is not yet complete. It may still have some unresolved addresses or references that need to be resolved through linking or further code generation. The object code has a few key characteristics. It cannot be executed directly because it has to be linked in order to execute, and it also has to be loaded into the RAM to be executed. But in turn, it still has some things that need to be resolved before execution can take place. And object code is usually linked with other object files or libraries. Now, if you remember from your AS level syllabus, libraries such as static link libraries and dynamic link libraries are where linking is relevant for, where you have to link the object code that you generate with these so-called library programs in order for the final executable to be produced. Then last but not least, object code is generated after code generation, which is the final stage of the compilation process. We'll be looking at 4 stages of compilation, and the final stage of compilation is code generation. In this final stage of compilation only is object code produced, which we'll look at. And object code is, anyway, part of this process before linking takes place. Then we'll take a look at intermediate code. An example of intermediate code used in Java is bytecode. But what exactly is intermediate code? Intermediate code is platform-independent, low-level code, which means unlike object code, it's not dependent on the software or platform. Sorry, it's dependent. It's not dependent on whether you're on a Windows machine or a Mac device or an Android. It's platform independent, but it is low-level code that is generated after parsing, but before the final machine code is generated, right? And it is often interpreted by hybrid systems or interpreted using kinds of hybrid systems. For example, in Java, we use a JIT compiler, just-in-time compiler to, compile the Java code, or Python would use an interpretation-based system to interpret the final level of Python intermediate code. So intermediate code can be executed either via an interpreter at the end, or it may use a hybrid of both, like an interpreted and a compiled system. And the characteristics of intermediate code is that it's not directly executed by the hardware, and it's executed instead by a virtual machine. In Java's case, this virtual machine is known as the Java virtual machine, or the JVM, but it's not executed directly by the hardware. It's executed by a virtual machine, which is what makes it so platform independent, because as long as you can install this JVM or virtual machine on any system, and essentially virtual machines can run on any host machine, independent of the host machine's hardware, right? For example, you can emulate other operating systems in within other operating systems to allow for software that would have been incompatible otherwise to run on certain devices. And this allows virtual machines to shine with intermediate code, because intermediate code is platform independent, because this intermediate code can be then run by a virtual machine irrespective of the underlying hardware. And then this enables portability across platforms, which you need to know. You need to know for the exam that intermediate code is portable across platforms. And last but not least, intermediate code allows for code relocatability, which means that code can be moved across different memory addresses, or the memory addresses of the code can be updated because it's executed by the virtual machine at a later point. It supports a wide range of libraries which can be linked during runtime. And it also allows for multiple programs to be linked during runtime, because at the end of the day, it's the virtual machine and the respective interpreter that's actually executing this intermediate code. It's not executed during compilation. And finally, we have our beautiful machine code, which is full binary code that can be executed directly by the processor. So you can understand that this is just usually in full binary form, and it's fully linked and fully resolved. So there's no unresolved or unknown references or addresses. All references have been resolved and all libraries have been linked. However, machine code is processor specific. So you can't get your Windows machine code, the one that that runs on your Intel chip, to run on an Apple Silicon chip. Processor specific is one key characteristic of machine code. And machine code can be loaded into memory directly and can be executed without additional processing. So as soon as you get machine code, you're down to the fetch execute cycle, where you can start executing this code through the normal fetch, decode, execute process. There's no need for additional processing. You can immediately load the machine code and run it then and there. Then last but not least, let's take a look at the compiler and interpreter, and what their so-called benefits and disadvantages, or what their key behaviors are. Let's start by looking at compilers. A compiler translates the entire source code into object code, right? Or you can imagine that this is machine code as well. But again, you know the difference, right? The compiler translates the entire source code into object code before execution. So it does not do it line by line like an interpreter does. It does it entirely at once. It does not execute the program while compiling. It checks the entire program at once. And if there are no errors, it produces the object code that can be run later, any number of times. But if there are errors, it lists them all at the end after the full code is checked. Now, this makes it a poor contender for debugging purposes because compiled programs show you all the errors at once during the compilation process's end or at the end of the compilation process, which makes it difficult for us to figure out errors if there are lots of them. And compilers build something called a symbol table. We'll look at what this means soon. And it does not require source code again and again after compiling successfully. So once you have the compiled program, you can keep running it without the requirement of the compiler software in itself. What's a symbol table? Now, to quickly remind you, or actually to quickly give you a definition of a symbol table before we officially look at it, a symbol table is a data structure used by compilers and also sometimes interpreters to store information about identifiers such as variables and constants in your source code. What that means is that during the compilation process, in order to convert the source code you've written into binary, the compiler needs to know what the different identifiers, variables, and constants you are using are. And in order to do this, it constructs a symbol table, which is a table that contains a list of all the identifiers that are used in your program. Hopefully that makes sense to you guys. We'll look at this in more detail later on. Now, an interpreter is the contender or the rival of compilers, where interpreters translate and execute. Keep that in mind. It translates and executes source code line by line directly. And a key feature of interpreters is that it executes the program while interpreting. It checks the code line by line and stops immediately on errors and reports them. It does not produce object code, and source code must be available every single time it runs. It also may build a symbol table, and it allocates memory for constants and variables during execution. So those are the key behaviors of an interpreter, where the main idea is that it executes while interpreting line by line and stops to report any errors, which makes it a perfect contender for debugging purposes. So compilers and interpreters can be quickly summarized using this table, where compilers, in terms of execution, execute after the entire program is compiled. Interpreters, however, execute during translation line by line. Compilers produce object code, which is machine executable, whereas interpreters produce no such intermediate or executable file. Compilers are faster because object code can be reused every single time without having to recompile the program, which makes it fast at runtime. But interpreters are slower because they have to translate your program every single time. Error detection isn't the strong suit of compilers because all errors are reported after compilation is over, whereas interpreters report the errors line by line and one error at a time during runtime, which therefore makes it excellent for debugging, whereas not so ideal in compilers because, compilers don't report you errors line by line. It shows you all the errors at the end. All right, that concludes our once and for all understanding of compilers, interpreters, object code, machine code, and intermediate code. If you have any questions, do drop them on the comment section below. And if you have any questions, do let me know and try your best to clarify them. And make sure that you guys understand this properly and effectively. But yeah, that's about it. Having understood this, we can now move on into the compilation process, which is one of the more core A2 level sections in this syllabus. Now, in this section, you're supposed to know how a compiler works. And in order to understand how a compiler works, we need to understand what stages a compiler takes to execute your so-called source code or to produce an object code file based on your source code, right? So in order to convert your source code into object code, the compiler follows a four-step mechanism. The first stage is called lexical analysis. The second stage is called syntax analysis. The third stage is called code generation. And the fourth stage is called optimization. The idea is the compiler takes in your source code, performs these four stages, and outputs a well-optimized object code, right? So keep in mind, guys, that a compiler would always go through these four stages to produce your final object code given the initial source code. Let's understand what these stages are and how these stages work. Lexical analysis, stage number 1. In lexical analysis, which is the first stage of compilation, the source code is scanned and broken down into tokens after removing any unnecessary characters like white space or comments. And the purpose of lexical analysis is to simplify the input for the next phase, which is syntax analysis, convert the raw source code into a token stream through a process known as tokenization, remove comments, tabs, new lines, and extra white space. And once and for all, one more important thing is that lexical analysis is conducted by a program called the Lexer. And the Lexer builds two important data structures called the keyword table and a symbol table. So if you remember from the previous simple definitions I gave you, a symbol table is essentially a table that contains a list of all the different identifiers you're using in your program. But what exactly is a keyword table, right? We haven't heard of that term before, haven't we? No, we haven't heard of that. Let's understand what keyword tables do. A keyword table is a data structure consisting of a list of keywords recognized by a programming language, which means that just like how a symbol table keeps track of all your identifiers, a keyword table keeps track of all the keywords, where it's a list of keywords that are officially recognized by the programming language. You can imagine that these are like the print keyword in Python or the if keyword in Python, any keyword that's specific to a language that falls under the keyword table. And each keyword gets a token, which is a number that's uniquely assigned to each keyword to thereby identify it. And it's also utilized in the tokenization stage to actually produce the final list of tokens. But again, don't worry about this too much, guys. We'll understand this in detail in the next walkthrough, where I'll walk you through a proper example from zero all the way to the end to help you understand how this first stage, lexical analysis, is applied to a real program or a real piece of code. Let's begin. Let's start off by looking at this sample Python code given to us. Imagine someone's written a Python code that says if mark is greater than 60, print pass. This is, I hope you guys agree, valid Python code. Now again, a quick disclaimer, Python code isn't really compiled, right? Python code is usually interpreted, but we're taking this as an example to understand compilation, just because Python is a language that most students might be familiar with. So in this process, when you're given Python code as your source code, what you first do is lexical analysis first identifies all lexemes, which is also why we call this lexical analysis, right? Lexical analysis is about working with lexemes. But what is a lexeme? A lexeme is the smallest meaningful unit in your source code. It's the smallest meaningful unit in your source code. As you can see on the left-hand side, I've put a box around each small unit or each smallest unit in your program. As you can see, the if condition is the smallest unit or a lexeme. The mark variable is a lexeme. The greater than sign is a lexeme, so on and so forth. So all the lexemes are identified by the lexical analysis stage, and I've shown it to you on the slide using those boxes. Step 2 is out of those lexemes, the lexical analysis stage, or specifically the lexer, will identify keywords. Keywords are reserved words defined by the programming language. And these keywords are recorded in something called the keyword table. So what you see in red color are the keywords or the programming language specific reserved words that are identified out of the lexemes that were initially identified by the lexer. And what we mean by building a keyword table is something like this. We create a table that contains a list of all the keywords and their respective tokens, which are unique numbers assigned to each keyword in this code. After this, we identify symbols. Symbols are identifiers and constants that appear throughout the code, and these symbols are recorded in a symbol table. And as you can see, mark, 60, and pass are examples of symbols because they are snippets of lexemes that you've specified as per your program. It's not programming language specific terms or syntax. It's words that you've created, symbols for variables and constants that you've used in your program. And these things appear in a symbol table where you have each symbol appearing as a row in this table. The type of each so-called symbol is also mentioned. So mark is a variable. 60 is referred to as an integer literal. Pass is an example of a string literal. And then moving on, you have a data type for every single symbol, where mark and 60 are integers, whereas pass is an example of a string. And these two also get tokens. So keep in mind, at the end of the lexical analysis process, you've produced a keyword table as well as a symbol table, where symbols are variables and constants that you've defined or identifiers, whereas keywords are Python specific or programming language specific terms, all of which get a token in a beautiful table. Step 4 is to tokenize, where each lexeme is converted to its respective token via the keyword and symbol table. And all the operators that we didn't look at, like the greater than sign, the colon, the open bracket, the close bracket, they are also assigned tokens based on a predefined operator table. Let's take a look at this. So here we have the keyword table. Here we have the keyword table. And on the right-hand side, you have the symbol table, which contains, your keywords and symbols as usual with the associated tokens. And then there's also an operator table, which contains a list of all operators identified or, regarded as operators by the programming language. Some programming languages may consider some operators that operate as operators. Some languages might consider some operators and as non-operators, right? So depending on the language, the operator table may change. But, it's like a predefined table that contains a list of operators and their respective tokens. And what happens is each of these lexemes are given their respective token from the respective keyword, operator, or symbol table, right? Keep in mind, the operator table isn't constructed, right? The operator table pre-exists. It's part of the language. So don't ever consider the lexical analysis stage to produce this operator table. It's only looked up to convert it into the token stream. So if it's converted into token number 1, based on the keyword table, mark is converted into token 50 based on the symbol table. And this process continues for every single token that we have, or every single lexeme that we have in our source code. And this, ladies and gentlemen, concludes stage 1 of the lexical analysis process of the compilation process, right? So at the end of the compilation process, you end up with a beautiful token stream as you see below. Now, lexical analysis can be summarized as following these 6 major tasks. It first removes white space, deleting unnecessary formatting and comments. It detects lexemes by breaking input into identifiers, operators, and blah, blah, blah. Tokenization by replacing keywords and symbols with tokens. Symbol table by recording user-defined names, types, and addresses. Builds a keyword table by mapping language-specific keywords into numeric token values. And outputs a token stream, which is then used by the syntax analyzer, also known as the parser, in the next stage. Right, let's begin. So the next stage, stage 2, is syntax analysis. What exactly happens in syntax analysis, guys? In syntax analysis or stage 2, which is the second stage of compilation, the token stream that was produced from lexical analysis is checked to ensure whether it follows the grammatical rules of the programming language. And in this stage, we verify syntax correctness and we build something called a parse tree or an abstract syntax tree. And we use this stage to help detect errors like missing parentheses or missing colons, incorrect statement structures, or misplaced keywords or operators. Let's take a look at what exactly syntax analysis is. But before we get there, let's try and understand what this so-called parse tree is about. A parse tree is a hierarchical diagram that shows how a sequence of tokens fit in a given grammatical structure of a programming language. So it's a tree, like a binary tree you could imagine, that contains a list of tokens and how those tokens are associated with each other. Now, let's understand the syntax analysis process with the token stream that we ended up with the previous code from Python, right? So imagine this previous Python code, which produced this token stream at the end of the lexical analysis stage, guys. Now, what happens in the first part of syntax analysis stage 2 is we compare these tokens with predefined syntax rules. And these syntax rules can be defined using syntax definitions like Buckers-Norm form or syntax diagrams. But let me show this to you in action. If you take this token stream, what happens is this token stream can be compared with predefined Buckers-Norm form rules. Like there might be a rule for an if statement, there might be a rule for a condition, then there might be a rule for a print statement, right? Now, if you take this token stream, each line represents each line of the respective Python program, right? If you take this first line of the token stream, which represents the if condition, we can cross-check the token stream to see if it matches the if statement B and F. So look at this, guys. If the if statement B and F says that for an if statement to be valid, there must be a token, specifically token number 1, and there must be a condition in the middle, followed by token number 11. And then what is a condition? A condition is defined here as an identifier followed by a token that is specifically token 10 and a constant. Let's see if this is correct. The if statement begins with token number 1, which is what is stated in the if statement BNF. And then there is some condition supposed to be there where the condition must begin with an identifier, token 10, and a constant. Let's see if that's correct. Now, here 50 is a reference to mark, which is actually a variable, or it could be considered as a valid identifier, which makes this part correct. And then 10 is token 10, which in this case is the greater than sign. And constant is essentially the 60 that has been defined here, which is an integer literal, which could be considered as a constant as well. And then that completes the condition part of it. And at the end, the if condition is closed off with a token number 11, which you can see here. So as you can see, by comparing the tokens with the predefined BNF, you can ensure whether the tokens are used correctly or if there's any errors. And you can proceed this for the entire token stream to ensure that all the tokens follow valid syntax. Now let's take an example of invalid token stream, one that doesn't have the correct syntax. Take a look at this code here. The close quotation and the bracket seems to be missing. And this is an error with the last line of the token stream, specifically the token stream line representing the print statement, right? Now, what seems to be missing is the close quotation and the close bracket, and that will be called by the print statement BNF. The print statement BNF states that it must begin with token number 2, which is a representative of the print command. Then it must be followed by token number 12, which is the open bracket. And it must be followed by 14, which is the open quotation. And then there is 52, which is the string literal, which is correct, right? There's a string literal here, the parse string literal. But seems like there's supposed to be a few more tokens, token 14 and token 13 to be precise, but they're actually missing in the token stream. That would trigger syntax analysis to fail because those tokens are missing, because the tokens are supposed to be there based on the BNF, but they aren't in the actual token stream. And that results in the syntax analysis stage, pausing or halting and reporting those errors as a syntax error back to the user. So that's how invalid syntax is detected by comparing the token stream with the BNF. But if this process is conducted successfully and you end up with a validated token stream, guys, you can then produce something called a parse tree using those validated tokens. Now, how exactly this parse tree is constructed is not part of the syllabus, but just to show you what the parse tree looks like, we can take each line of our program. Let's take line number 1, and we can build a hierarchical structure for it, where the if condition might be the first root node, and under this if you might have an expression which might have the greater than symbol in the next root, where you might have mark below that and 60 to the right of that. And then you might have some kind of so-called nested tree structure for the print statement, or you might have a completely different tree for the nested code block, the print parse section. But the idea is that for the print parse section, there might be, some code or some tree structure which represents print as the root node, followed by the so-called brackets as the left and right nodes. And maybe there are some middle nodes to represent the string literal parse. But again, the structure of this itself is not part of the syllabus, but the idea is that you take your validated token stream and you essentially construct these hierarchical diagrams to represent how each token is represented or related to other tokens, so that the overall next stage that we have, specifically this code generation stage, can understand how each code block is related to one another, because then you can run tree algorithms to convert this parse tree into valid code. So the idea is that you take your tokens from the validated token stream and you convert it into a tree structure to represent the relationships between the tokens, which can be done either line by line, or it can be done to essentially map multiple lines together to form one big token parse tree as well. But that's the idea, guys. A parse tree is essentially a representation of tokens to other tokens. And then Having done this, we can quickly look at a summary of syntax analysis. And in syntax analysis, guys, you have 5 main stages where you first input the token stream from lexical analysis. You pass it to check if grammatical rules are being measured and check if the sentence structure is correct. If there are any issues, by cross-checking it with predefined rules such as in BNF, you can report those syntax errors like missing colons or operators, and then you can produce an abstract syntax tree or a parse tree, which is used in the code generation stage, which is the next stage. And then the output will be the parse tree or, if any error messages as well. Finally, we hit the code generation stage, stage number 3, which is the third stage of compilation, where the validated parse tree is converted to low-level code, which is typically object code or intermediate code. In this stage, we translate the program from the parse tree into a machine-readable form, and it prepares the program for linking and execution. And this stage can either produce object code, which is platform-specific binary, which needs to be linked, or it can produce intermediate code, which is portable bytecode for virtual machines, which then needs to be interpreted. Again, the route we use depends on the actual kind of programming language that is responsible for this task. But having said this, we then move on to stage 4 optimization, which is the final stage of compilation, which is used to increase the efficiency of the generated object program without changing its output or logic. In the optimization stage, our goal is to make the object code faster, smaller, and more efficient. And it's also used to reduce resource usage, such as CPU cycles, memory, and execution time. And the overall stage 4 helps improve performance, especially in loops, by removing repeated expressions or redundant operations. Again, this is the process of optimization. It's to make the program more efficient. And at the end, optimization happens after code generation, or it happens before or during linking, and it may also happen at runtime in systems like just-in-time compilers. So, for example, if you use intermediate code, such as in Java, during the intermediate code execution as well, optimization can happen. But to give you an overall idea of optimization, let's take a look at this program here. W equals x plus y, and then v equals x plus y plus z. Now, if you take these two lines of code, guys, the assembly code for this might look like this: LDDX, load x, add that to y, and store the result to w, which completes the first line. And then LDDX, ADDY, ADDZ, and store v, which completes the second line, right? Again, take a pause of this video to understand how the assembly code lines correspond with the high-level code lines at the top. But if you have any doubts, do let me know. Now, I hope you can understand that in this program, there is a redundant snippet of code. Can you identify that? Basically, do you have to say v is equal to w, v is equal to x plus y plus z, or could we use w in the calculation of v? Turns out you can, because w is x plus y. So you could replace this x plus y with w instead, right? And as a result, you're making these two instructions dependent, right? You're making the first instruction, you're forcing the second instruction to be dependent on instruction number 1. But again, keep in mind, guys, that if you're focusing on making sure that the two instructions are independent of each other, then you may have to not do this optimization, especially in cases like parallel processing, where you need to make sure that instructions are independent. But if you want to make sure that your instructions are as optimal as possible and you don't care about independence, then you can replace the x plus y in the second line, the v equals x plus y plus z line. You can replace the x plus y with w, essentially reducing the redundancy. And if you do this, you can basically remove this x plus y with w, replace it with w, and thereby cut down one of the steps in this process to instead say LDDX, ADDY, STOW, and then you could say LDDW, right, to load w from the memory location that it was stored, and then add that to Z and then store the result in V. As a result, optimizing the overall program and making the program much more efficient. Again, it is not an incredible efficiency, but you can see how these optimizations add up when you have larger and larger instructions to work with. So this optimization stage is the final stage of compilation, where you input your initial object code, identifies efficiencies and removes redundancies to output faster object code with same logic but better performance, with the goal of fast execution with less memory or CPU use. That, ladies and gentlemen, completes Translation Software Unit 16 from the Cambridge 1918 A2 level Computer Science syllabus. Good luck for your exams.